In the previous video, we have learnt about the basic Norrish type 1 reactions. Now let us learn some advanced Norrish type 1 reactions in acyclic, symmetrical, saturated carbonyl compounds and acyclic, unsymmetrical, saturated carbonyl compounds. First, let us see acyclic, symmetrical, saturated carbonyl compounds. Let's take the example of 3-pentanone, which consists of CH3, CH2 double bond, CH2, C double bond O, CH2 and CH3. This is 3-pentanone. It is acyclic because it has no ring in its structure. It is symmetrical because equal number of carbon atoms on either side of the carbonyl group, or same alkyl groups, that is CH3, CH2 or C2H5 are present on either side of the carbonyl group, that is C double bond O. It is called saturated because only singly bonded carbon atoms except the functional group C double bond O is present. As you all know, this is a carbonyl compound because this is a compound having carbonyl group, that is C double bond O as the functional group. This compound CH3, CH2, C double bond O, CH2, CH3, it has 2 alpha bonds. This is one alpha bond and this is another alpha bond on either side adjacent to the carbonyl group. This is the carbonyl group, C double bond O. This is an alpha bond and this is another alpha bond. Since it is symmetrical, any one of the 2 alpha bonds can be cleaved. So let's see the primary process. In the primary process, upon irradiation by UV light, the compound undergoes Upon irradiation by UV light in the range 230 to 330 nanometers, the carbonyl compound undergoes homolytic cleavage of alpha bond in N2pi star excited states, both in the singlet and triplet states, to form intermediate free radicals. So this is the primary process in which we get free radicals. Let's see how it happens. CH3, CH2, C double bond O, CH2, CH2. 3. It is in ground state. SO is ground state. When it is irradiated by UV light, it is excited to N2 pi star transition and enters S1, that is singlet excited state. From singlet excited state, through intersystem crossing, it enters triplet state. So in the triplet state, the alpha bond, one of the alpha bonds, let's take this side. This alpha bond cleaves homolytically to form 2 radicals. This bond is made up of 2 electrons. So one electron will go to this carbon atom to form a free radical, and another electron goes to this carbon atom to form another radical. As a result, we get CH3 CH2 C double bond O radical, which is acyl intermediate free radical, and CH3 CH2 free radical, that is alkyl intermediate free radical. As you all know, these intermediate free radicals are unstable because each carbon radical has 7 electrons only. So it needs one more electron each to become stable, to complete the octet, because 7 electrons are not stable. So these intermediate free radicals undergo various reactions to give different products depending on the conditions of the system in the secondary process. Let us see the secondary process. Secondary process is product formation process. First process is decarbonylation. Decarbonylation means removal of carbon monoxide from acyl free radical at high temperature to give an alkyl radical, CH3 CH2 C double bond O. This bond between CH2 and C double bond O cleaves homolytically to give CH3 CH2 radical plus carbon monoxide. This CH3 CH2 radical is called alkyl radical. Dimerization of these two alkyl radicals to give us an alkane, that is CH3 CH2 radical, which is an alkyl free radical, combines with another alkyl free radical, CH2 CH3 radical. These two radicals will come together to form a new bond, forming CH3 CH2 single bond CH2 CH3, which is an alkane. In this case it is butane. That new bond is represented by red ink. Okay. Now, coupling or recombination or dimerization of two acyl radicals will occur to form a diketone at low temperature. Remember, decarbonylation takes place at high temperature and diketone formation takes place at low temperature. CH3 CH2 C double bond O radical, that is acyl free radical, will combine with another CH3 CH2 CO double bond, another acyl free radicals, to form CH3 CH2 C double bond O single bond C double bond O CH2 CH3, which is a diketone. Here it is hexadione because it has 6 carbon atoms and 2 carbonyl groups. So it is hexadione. Next, disproportionation or intermolecular hydrogen abstraction between acyl radicals to form an aldehyde and a ketene. Disproportionation occurs. CH3 CH2 C double bond O radical, acyl free radical, and another acyl free radical, CH3 CH2 C double bond O. This CH2 is written as H and H. The bond between this carbon and hydrogen cleaves and forms hydrogen along with its electron, and this electron goes to this carbon atom. This hydrogen along with its electron is abstracted by this acyl free radical. So this acyl free radical is written like this: C double bond O, C, H, H and CH3. The bond here cleaves, forming radicals. One radical is with this carbon atom, another radical with this hydrogen. This hydrogen along with this radical is abstracted by this carbon atom of this acyl free radical. As a result, CH3, CH2, C double bond O will get hydrogen radical here. Both of them will form a bond, that is an aldehyde, CH3, CH2, CHO, which is an aldehyde. Okay. The remaining carbon atom has one radical here and one radical here. Both these radicals will combine to form another bond. So this C double bond O and CH will have double bond. That is ketene. So as a result of disproportionation, we get an aldehyde and a ketene. Then hydrogen abstraction by alkyl free radical. So hydrogen is abstracted by acyl radical from alkyl radical. CH3, CH2, C double bond O is the acyl free radical. CH2, CH3 radical is alkyl free radical. In the alkyl free radical, the bond between carbon and hydrogen is cleaved, as a result of which there is another radical formed at this carbon, and this hydrogen along with its radical is abstracted by this C double bond O radical. So as a result of which we will get CH3, CH2, C double bond O and hydrogen, which is an aldehyde. The two radicals of this carbon will form a bond, another bond here, that is CH double bond CH3, which is an alkene. So because of the hydrogen abstraction by acyl free radical, we get an aldehyde and an alkene. Next, hydrogen abstraction by alkyl radical from acyl radical. There it was acyl radical from alkyl radical. Here alkyl radical extracts a hydrogen from acyl free radical. CH3, CH2 radical is alkyl free radical. CH3, CH2, C double bond O is acyl free radical. Here the bond between carbon and hydrogen cleaves, forming a radical here and a radical here. This hydrogen along with its radical is abstracted by CH3, CH2 radical. So as a result of which we get CH3, CH2, H, that is CH3 single bond CH3, which is an alkane. In this case it is ethane. Then the two radicals will form another bond here. So C double bond O double bond CH CH3, that is ketene. Ketene is formed. So we get an alkane and ketene. Now let us consider acyclic, unsymmetrical, saturated carbonyl compounds. Let's take an example of 3,3-dimethyl 2-butanone. This is a butane because it contains 4 carbon atoms. It contains a carbonyl group, so it is called butanone. Then to the third carbon atom, 2 methyl groups are connected, so it is called 3,3-dimethyl 2-butanone. Okay, it is acyclic because the structure has no ring. It is unsymmetrical because different alkyl groups are present on either side of the carbonyl group C double bond O. Left side of the carbonyl group is CH3 group. On the right side of the carbonyl group is CH3 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 group. Okay, next it is called saturated because only single bonded carbon atoms are present here except the functional group C double bond O. It is a carbonyl compound because it is having a carbonyl group, that is C double bond O as functional group. Now let us see how many alpha bonds it has. CH3 C double bond O, C, CH3, CH3, CH3 has 2 alpha bonds, A and B. It has 2 alpha bonds, one on either side of the carbonyl group. If A alpha bond is cleaved, we get CH3 radical and C double bond O, CH3, CH3, CH3 radical, which is a primary radical, and this is a methyl radical. If B alpha bond is cleaved, we get CH3 C double bond O radical and CH3 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 radical, which is tertiary radical, and this CH3 C double bond O is primary radical because this carbon atom is attached to another carbon atom. This is tertiary carbon radical because it is attached to 3 more carbon atoms. Stability of the radicals, as you all know, tertiary is more stable than primary, tertiary is more stable than secondary, than primary, than methyl radical. So that alpha bond cleaves, which gives more stable radicals. So here B alpha bond cleaves. Let us see the primary process. In the primary process, upon irradiation by UV light in the range 230 to 330 nanometers, the carbonyl compound undergoes homolytic cleavage of that alpha bond, which forms more stable free radicals in N to pi star excited state, both in the singlet and triplet excited states. Here CH3 C double bond O, CH3 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 is in ground state, S0 ground state. When it is irradiated by UV light, it gets excited from N to pi star transition and enters singlet state S1. From singlet state, through intersystem crossing, it enters triplet state. In the triplet state, this side of the alpha bond cleaves to form a tertiary radical and a primary radical. So this alpha bond cleaves to form CH3 C double bond O radical, which is acyl intermediate free radical, and CH3 radical, which is alkyl intermediate free radical. As these free radicals are unstable, they undergo various reactions in different conditions to form different products in the secondary process. These free radicals undergo various reactions in different conditions to form different products in the secondary process. Let us see the secondary process. Secondary process, product formation process. First, decarbonylation, removal of carbon monoxide of acyl intermediate free radical. This occurs at high temperature and in gaseous phase. CH3 C double bond O in presence of UV light at high temperature and in gaseous phase. This bond between CH3 and C double bond O undergoes homolytic cleavage to form two radicals. One is CH3 radical, that is alkyl radical, and this radical will combine with this to form CO gas. Then dimerization of two alkyl radicals to give an alkane, CH3 radical and another CH3 radical will form a new bond to give CH3 single bond CH3 alkane, which is ethane here. Then CH3 radical, that is alkyl radical, will combine with another free radical formed in the primary process, that is CH3 radical. This is also an alkyl radical. These two radicals will join to form a single bond. So we get an alkane, CH3 C, CH3 and CH3. This is 2,2-dimethyl propane. 2,2-dimethyl propane, because two methyl groups are attached to the second carbon. Next, coupling of acyl free radicals to form a diketone at low temperature. So at low temperature, two acyl free radicals will combine. CH3 C double bond O will combine with another CH3 C double bond O to form CH3 C double bond O single bond C double bond O CH3, which is diketone. Here it is butadiene because it has 4 carbon atoms. It is called buta, and dione because it has 2 carbonyl groups. Next reaction is disproportionation, that is intermolecular hydrogen abstraction between two acyl radicals to form an aldehyde and ketene. CH3 C double bond O radical will and CH3 C double bond O radical. This CH3 C double bond O, we have written hydrogens like this, C, H, H and another H. This bond between this hydrogen and carbon cleaves, As a result, this hydrogen is abstracted by this acyl free radical to form an aldehyde, CH3 C double bond OH, and this carbon has a radical here, and this carbon will get another radical here. These two radicals will combine to form another bond here. So it will have C double bond O double bond CH2, that is ketene. So as a result of disproportionation, we get an aldehyde and ketene. Hydrogen abstraction by acyl radical from alkyl radical. You need not know the products here, because if you do the reaction you will get the products. So remember, acyl radical, hydrogen abstraction by acyl radical. So this is the acyl radical, CH3 C double bond O is the acyl radical. It extracts hydrogen from alkyl radical. So alkyl radical is written like this: CH3 CH3 C CH CH CH. Okay. So this bond between this carbon and hydrogen cleaves. One electron goes to this carbon, one electron goes to this hydrogen. Now this hydrogen along with this electron is abstracted by this acyl radical, and this carbon is already having one radical and this carbon is having a radical. These two will form a bond, as a result of which we will get CH3 C double bond CH2 and CH3, that is an alkene. Here we get CH3 C double bond O, and the hydrogen has come and joined here, so it forms an aldehyde. Now let us see. We have first seen hydrogen abstraction by acyl radical. Now hydrogen abstraction by alkyl radical. From where it will get hydrogen? From acyl radical. So this is the alkyl radical. CH3 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 radical. This is alkyl radical. It will get hydrogen from acyl radical. C double bond O single bond C CH H H. The bond between this carbon and hydrogen cleaves. As a result, we get two radicals, one radical on the carbon atom, one radical on the hydrogen atom. This hydrogen along with this radical is abstracted by this alkyl radical. As a result, this hydrogen gets attached to this alkyl radical, forming an alkane. This carbon is having one radical and this carbon has now got another radical. These two radicals will join here to form another bond. So we get C double bond O double bond CH2, which is ketene. So I hope you understood these reactions. In the next video we shall discuss Norrish type 1 reactions in cyclic carbonyl compounds. Thank you.